The second of our trig substitutions is going to involve substitutions of the type u equal a tangent theta, where theta is strictly between negative pi over 2 and pi over 2. Probably some discussion of that range of values is in order. The graph of the tangent function has period pi radians and has a vertical asymptote whenever the input is an odd multiple of pi over 2. So if you were trying to solve the equation tangent of theta equals 3, there is an infinite number of solutions. The x-coordinate that goes with this point, for instance, or the x of that point, or of that point. On the other hand, if you restrict your attention to the part of the graph at tangent that lies between negative pi over 2 and pi over 2, there is only one point on that graph with y-coordinate 3. There will only be one solution of tangent of theta equals 3 in that range of theta values. If you remember your trigonometry, this is the range of theta values that you use to construct the arctan function. So this particular solution that I've drawn an arrow at is actually theta equals arctan of 3. This piece of the graph of tangent theta takes on all values that tangent can take on. There are no repeats, and that's what guarantees that there's an inverse function. This has an additional benefit, which we'll talk about next. We will use this substitution typically when I have expressions involving a squared plus u squared, where u is some expression involving x. Under the current circumstances, I need to know what that radical is, so let's calculate that. Doing the usual algebra, I find out that the radical must equal a times absolute value secant of theta. Within the range of theta values that we're talking about, though, cosine is positive, the secant is the reciprocal of a positive number, secant of theta is positive, and just as with the other substitution, I can dispense with the absolute value sign. By choosing theta to lie strictly between negative pi over 2 and pi over 2, radical a squared plus u squared, under the substitution u equal a tangent theta, always reduces to a times secant theta. As an example, let's look at integral square root 1 plus 4x squared dx. The quantity underneath the radical sign could be written as 1 squared plus the square of 2x. I'll think of the a as being 1, the u as being 2x, and since I'm supposed to make u equal a times tangent of theta, I'll let 2x equal tangent of theta, where theta is in the specified range of values that we have previously discussed. We already know what the radical is going to work out to be, but we'll calculate it just as a sanity check. The expected answer was that the radical would be a times secant theta. Since a is 1, that would be 1 times secant theta, which is what we get. We mustn't forget to take care of the dx, though. Writing in all the relevant bits, I find out that I have to integrate 1/2 integral secant cubed theta d theta. This is an odd power of secant alone. If you'll refer back to previous videos, you'll see that we've already done that integral at least twice, so I'm just going to reuse that result. Writing in the result that we had previously, 1/2 times 1/2 is 1/4 of secant theta tangent theta plus natural log absolute secant theta plus tangent theta. This is my answer, except it's in terms of theta, not x, so we have to take care of that too. We could do the right triangle thing, or we could look back to calculations that we have already done. Firstly, tangent of theta is 2 times x. Secondly, radical 1 plus 4x squared in the end worked out to be secant of theta. So for this one, we already know what tangent of theta and secant of theta are. No need to draw the right triangle in this case. So by doing this substitution involving the tangent function, we're able to get our hands on an antiderivative that previously was beyond our capabilities. As another example, let's look at the integral of x cubed times radical 1 plus x squared with respect to x. The thing to take note of is the 1 plus x squared. That is 1 squared plus x squared. I'll let the a be 1. I'll let the u be x. My substitution, u equals 1 times tangent theta, will then just be x equals tangent of theta. The derivative of x with respect to theta would be secant squared theta. So dx is secant squared theta d theta. I now know everything in my integral except for the square root, but based on our previous comments, I predict that the square root will work out to be secant of theta. We should do a check on that to make sure that it's correct. If I didn't know what range of theta values I was in, I would have to write down absolute value secant theta, but within the specified range of theta values, cosine is positive, therefore so is the secant. To find the antiderivative in terms of theta, I have to evaluate the integral of tangent cubed theta, secant cubed theta, d theta, but we have a recipe for that, so we'll use a method from the previous sections. The suggested procedure is to split off a factor of tangent theta secant theta. That quantity is the derivative of secant theta, which suggests that I express everything else in the integral in terms of secant theta, so that we can then do a substitution. Everything is already set up except for the tangent squared of theta, but one of our trig identities tells us that tangent squared is secant squared minus 1, so we will use that substitution here. After making the indicated substitution, this turns into a problem that is very easy to do. When I multiply out the integrand, it will be a polynomial in terms of u, and this is one of our most basic integration techniques. Antiderivative in terms of u is 1/5 u to the 5th minus 1/3 u cubed plus a constant. The substitution was that u was secant of theta, and earlier in this problem we saw that secant of theta was the square root of 1 plus x squared. If we like, we could express that first term in terms of the 5/2 power of 1 plus x squared, and the second as the 3/2 power of 1 plus x squared, and then we could factor some things out to try to make it look a little nicer. However, this is a correct answer, so I'm just going to leave it like that. Lastly, let's look at the integral of 1 over radical 4x squared plus 4x plus 5 with respect to x. At first glance, this doesn't appear to fall into any of the categories that we've been talking about, but by manipulating it a little bit, we'll see that it actually is. To begin with, I'll separate the 5 out because it's just a distraction to me. In what remains, I have 4x squared plus 4x. I'll factor the 4 out in order to make the coefficient on the x squared equal to 1. I have x squared plus x inside the parentheses. I'm going to complete the square on that. I'm going to take the coefficient of the x to the first power term, which is 1, divide it by 2 to get 1/2, square that to get 1/4, and then to complete the square, I need to add 1/4 to x squared plus x. My desire for doing that is to achieve a perfect square, but of course there's a little bit more to it than that. The quantity that I've written on this new line is not the same as the one on the previous one, unless I correct for that addition of 1/4 in some way. This looks slightly nonsensical, because inside the parentheses one could cancel the 1/4 out and then recover what we had before, but we have a reason for doing this. X squared plus x plus 1/4 is a perfect square. This is beginning to resemble something that we know about. I've got the square of some expression, namely x plus 1/2, but there's all these other numbers and quantities to account for, so let's go ahead and simplify this. Using properties from algebra, it turns out that the quantity underneath the square root sign is 4 plus the square of 2x plus 1. This is of type a squared plus u squared. If I think of the a as being 4 and the u as being 2x plus 1, we're going to make the substitution u equal a tangent of theta. That means that 2x plus 1, that's the u, needs to be 2 times tangent of theta, since a squared is 4, meaning that a is 2. Making the indicated substitution, we already know what the radical in the denominator is going to work out to be, but just for practice, do the algebra, it works out to be 2 times secant of theta. In addition, we have to figure out what the dx is as well, and this is slightly different from what we've done in the past, so that needs to be done in some detail. After doing the usual kind of calculations, it turns out that dx is secant squared theta d theta. Writing in all the little bits, I have to calculate 1/2 times the integral of secant theta d theta, but that integral is on the list of things that we know how to do. This is my antiderivative, except for the fact that it's written in terms of theta, and I need it to be written in terms of x. I need to go back and look at the relationship between theta and x. 2x plus 1 was equal to 2 times tangent theta. That means that tangent of theta is half of 2x plus 1. There are lots of different ways that I could write that down, the easiest one of which is tangent of theta is opposite over adjacent, so I'll make the opposite side 2x plus 1 and the adjacent side 2. Since I have a right triangle, figuring out the length of the hypotenuse will be easy. Tangent of theta will be 2x plus 1 over 2, and secant of theta will be radical 4x squared plus 4x plus 5 over 2. Taking advantage of those facts, I can write my answer finally back in terms of the x variable, and therefore achieve our goal. This has been the second of 3 different types of trig substitutions. Both of them have been relatively nice in the sense that after we figure the radical sign out, there is absolutely no ambiguity involved with that absolute value. In the next video, we're going to look at the third type, and then we're going to have an issue with that. It won't be too difficult to take care of, though, and then we will have 3 different types of trig substitutions that we can take advantage of when we can. I hope everyone's having a good day, and I'll talk to you again soon.